I should just start. So, yeah. Good. So this is my second week-long visit to the Institute, and it's been a wonderful experience. So I want to start by thanking Vladimir and Steve and Thierry for planning this special year and making me part of it. It's been wonderful. Let's see. So I should start by emphasizing that this is joint work. So the title of the talk is the title of a paper that Chris Kapulkin and Peter Lumsdaine and I are working on together. So I'm really reporting on this joint work. I put a quick characterization or summary of the project. So what we're doing is we're formalizing elementary homotopy theory. A notable aspect is that in the formalization, we're really only using a fairly restricted fragment of dependent type theory. So I'll spell that out later on. And finally, everything that I tell you that we formalize has been verified in Coq. So it's a formal development in Coq. And at the outset, I should make it clear that both Chris and Peter have an understanding of homotopy type theory that is far deeper and far broader than mine. So they've been very kind these past few months to put up with me, and I'm hoping that you'll bear with me as well while I try to report on what we've done. The mathematical content of what I'm about to tell you is simply that certain statements expressible formally in the language of dependent type theory can be derived in a certain axiomatic framework. And so let me start by, so here's the outline of the talk. I'm going to start by giving you an explicit description of the axiomatic framework, what we're using of dependent type theory. And I'll say a few words about the intended semantics. And then I'll spend some time just giving you an overview of all the things we've formalized. It'll largely be in a laundry list of facts and so on. But in a sense, I want to advertise what we've done. And then I'll spend some time just sort of reflecting on the formalization, giving you some additional detail about what the challenges were and how we met them, some examples of proofs, and how we went them, and some just general observations about the formalization process. Feel free to interrupt with questions or comments as I go. So let's do that. So the first thing I said is to tell you about the logical setting. So here it is. Here's what we use. So we use pi types with all the usual formation rules, introduction elimination rules, and beta computation rules. Sigma types. With or without betas? I'll come back to that in a minute. OK, so for the moment, not yet. I haven't said eta yet, so far just beta. So pi, sigmas, and the path types with the usual inductive characterization. And we use functional extensionality in a major way. So this is, so it's 4 dependent functions, but the axiom that says if f and g are pointwise equal or homotopic, then they're homotopic. Oh, so this reminds me, I will go back between notation, equality. I'm going to be totally unprincipled about notation. So I'll use, I don't know, as the mood strikes me, I might use equality, I might use path, and so on. But it all means the same thing. And then, to be honest, so in fact, Coq does implement the eta conversion rule for pi types. And it's often convenient to use, and so we do. At the same time, we're pretty sure that nothing we use crucially depends on it. So I sort of would put this in bracket. But again, I'd be lying if I said we didn't, because it's in Coq, and we do use it.
Propositionally, it follows from practice.
Yeah, so propositionally, right. So propositionally, it follows from function extensionality. I don't know of any conservation result that says that adding it as a computation rule doesn't make a difference. But so anyhow, so we use it. And I'm going to add a little bit more to the list. But at this point, I want to emphasize that the vast majority of what we do uses just this. Okay, nothing more than this. And so this is really as close to pure logic as one can hope to get in homotopy type theory. So that's really the point, that we've really tried to get by with sort of a bare minimum and see how far we can get. So OK, so now then, OK, so specific types. Let's see, I guess we do use, yes. So we do use unit, thank you. So that comes in early on. Otherwise, later on in some of our examples, we use bool. and we use the natural numbers. But that's really just usually when we want to construct particular examples and so on. So even those get used in just a mild way. And the other thing we use sometimes is a universe. So a single universe of types. And I'll expand on this later. We use that to express the universal property for pullbacks and limits and so on. But then we show that there's an equivalent formulation of those universal properties that don't make use of U. So U does come in, but in part, we bring it in to show that, in a sense, it's eliminable. So the point is there are no higher inductive types. There are no resizing, no univalence. So in a sense, this is sort of counter to some of the directions that have been pursued this year in sort of seeing how you can extend the type theory. Again, the project is to see how much homotopy theory you can actually do with just a fairly minimal framework. And the answer is that it's a fairly surprising amount. Let's see. So to give this a name, because in proof-theoretic terms, you would do something like you would write down, Martin-Liff type theory, which you typically take to include, pi sigmas and paths, and then you would say, plus functional extensionality, plus maybe eta, plus the universe, plus the Booleans, plus natural numbers. I guess I should put, well, take unit to be part of Martin-Liff type theory. And so in the paper, we call this FML for fibration ML, and I'll give the reasons for that in just a moment. And that's just to have a name for this, because we want to say that we've derived things in this formal theory. But again, much of it uses just the first component. OK. So let me say a few words about the intended semantics. So morally speaking, what we have in mind is something like fibration categories in the sense of Ken Brown, 1973. So Brown called them categories of fibrant objects. The title of the paper, so the title of our talk is a nod to his paper. So let's see, where is it? The title of the paper was Abstract Homotopy Theory. And generalized sheaf cohomology. So we have nothing to say about generalized sheaf cohomology. Not yet. OK, very good. But the story, so as Chris explains to me, what Brown was trying to do was in developing generalized sheaf cohomology, the point is he was working with a collection of things without a lot of structure. And so what he asked was, what's the bare minimum one needs to have axiomatically in order to do homotopy theory? And this was his answer. He just wrote down a list of axioms and said that's what we will use. And so let me quickly tell you what a fibration category is. I don't want to dwell on it because it's not the topic of the talk. But let me just at least say it because it'll be meaningful to some of you and probably more meaningful than it is to me. But so a fibration category is just a category with two distinguished collections of arrows. So W for weak equivalences and F for fibrations. And then it's satisfying, well, some axioms. Right? And so I won't write them down, but let me just sort of tell you what they are. So Brown, the first axiom was a 2 out of 3 property. So if you have a composition of 2 arrows, if you have a, so one, so if you have a, yes. So what is, it? So given Fg and F composed with G, if any two of those are weak equivalences, then the third is as well. That's recently been upgraded. People now talk about a 2 out of 6 property, which is like a 2 out of 3, but better. Right, so we'll take that to be the new definition. The second axiom says that isomorphisms in the category are acyclic fibrations, which means exactly that they're both weak equivalences and fibrations. Okay, so every isomorphism is an acyclic fibration. The category is required to have a terminal object 1. the category is required to have pullbacks along fibrations. And moreover, fibrations and acyclic fibrations are stable under pullback. And finally, the last axiom is that the diagonal map from any x to x, the x cross x, factors into a weak equivalence followed with a fibration. So the idea is the thing in the middle is you think of that as being a path object. So every x is equivalent to a path object, which has a projection to x cross x. Okay. Now, one thing that we did as sort of preliminary to the formalization is we show that, so here's the fact. So we show that every categorical model of our theory FML has the structure of a fibration category. And so by categorical model, I mean just in the conventional sense today. So for example, in terms of the semantics of type theory in terms of contextual categories, every such model of the axioms FML has the structure of fibration categories where you take F to be those arrows that are isomorphic to a composite of projections. And then the weak, so projections of sigma types. And then the weak equivalences are just the weak equivalences in the sense of homotopy type theory. So I'll remind you that F from A to B is a weak equivalence if for every y in B, the homotopy fiber over y is contractible. Okay. So take any categorical model of the system I described above. In fact, you don't need the universe, just the basic stuff. Take those to be the fibrations, those to be the weak equivalences, and you have a fibration category. Yeah.
So the notion of a model here is, just occurs to me that it's a slightly different meaning of the word model. I mean, a model may be just a functor. And
Okay.
the target category need not have any of them. Here it's more like a, like a type system is identified with the corresponding essentially algebraic theory.
Yeah.
We're talking about a model of the theory,
That's right.
which will be then a contextual category with all the structures of it.
Yeah.
Right?
Is that right? Yeah, my guys are nodding. So.
I agree that this theorem is not so clear as the way it's stated here. It's not so obvious what it means to say that contextual category is a fibration category. Do you mean that the syntactic category?
So if you take the
Contexts
so I think, and these guys will help me out. I mean, if you just take the underlying category, and you identify that, this is your class F of fibrations. This is your class of weak equivalences. Then that category with this and that satisfies all the properties of is a fibration category in that sense.
in the image of the functor has to be, for example, not everything has to be in the image of the functor, so it's
Right.
not going to have the structures.
But we do say arrow is isomorphic too. And so this isomorphic is in the external
Talking about two different
sense.
versions of a model.
By a categorical model, as Vladimir says, what we mean by a categorical model is a contextual category carrying this algebraic structure. We do mean not just the functor, but the whole category carrying the structure on the whole category. So by a categorical model, that's what we mean.
Yeah, we probably need a better word for it because that's confusing. It's like the first time that I myself understood what exactly is meant by that. But I always looked at it and I was kind of perplexed.
Do you mean something like the category of context itself?
I don't know. What is meant
a
is a
fibration
category carrying all this. What it means is that a category such that using its objects and morphisms, you could apply to them phi's and sigmas and all of that stuff.
Has all that stuff.
Yeah.
Then it will be
Yeah, so it's a category
Maybe,
on which you can operate as if this were context.
maybe we could call that a contextual model or something
Yeah,
like this.
we'll think about it.
there's lots of terms.
Okay, let me not get bogged down here because this is really not what I want to.
Does this result follow from the theorem of Gambino and Garner?
So that I don't know. So Mike, well,
As a whole, it doesn't, but parts of it are certainly the same thing.
yeah. I mean, it's not a very hard thing to show. I mean, basically, the way we argue this is a mixture of internal and external reasoning. I mean, even to describe this, you have to talk about isomorphisms in the category. So that's an external notion. But basically, what we do is we write down the axioms internally in the language of type theory. We prove them from the axioms. So that's part of our formalization. And then there's this sort of this meta-theoretic argument that basically the fact that we verified the axioms internally says what we, says what you want them to say.
Sounds like the theorem of Gambino and Garner to me.
Well, it's a different statement. It's a very close related theorem. It's got the same sort of ingredients and so on, but it's just a different set of
I think in light of the fact that those two authors are here, we should acknowledge.
Okay. So the acknowledgement is that this is closely related to, and perhaps even follows from, the theorem of Gambino and Garner. Okay, good. Okay. Now, I don't want to make too much of this. So certainly, if we can derive a statement from the axioms of FML, then it will be true in any it'll be true in any model of FML. So in particular, it'll be true in any fibration category that has enough structure, to model this type theory. And conversely, if you have a fact that's true in all such fibration categories, then in particular, it will be true of the syntactic category, and hence derivable from FML. So it sounds sort of like a soundness and completeness claim, but it's not really that, in the sense that I mean, what I've really just said is that the axioms are sound and complete for models of FML, which doesn't say very much. The problem is that right now it seems hard to give a nice homotopy theoretic characterization of what the relevant vibration categories are. So that's why I started out by saying that morally speaking, this is the intended semantics. Again, in precise terms, all we can really, all I can really say right now is that anything we prove from FML is true in all models of FML. But the point is, because FML is fairly restricted, we expect that they should have interesting homotopy theoretic interpretations. So certainly, anything we derive is true in Vladimir's simplicial model. But the expectation is that they should be true, that they should hold more widely. Okay. So let me move on to the second part, and now just try to give you an overview of all the things we formalized. And I guess let me leave that up a little bit longer, and then start building the list on this blackboard. So this is the contents of the formalization. And so what's up on that board is a dependency diagram of all the files. So we build on top of the homotopy type theory, the hot library. We have a file of auxiliary effects that we proved along the way that weren't in the library, but could have and perhaps should have been there. And then the third file up there, which I called fundamentals, is related to this claim that I just described. That's where we basically derive all the axioms for vibration categories formally. So let me leave that all in the background. And then so here's what's in the rest of the library. So let me start with pullbacks. So again, the idea is this is elementary homotopy theory. So we have the standard construction of the pullback, as just the well, let me have a picture up just to have things to point to. So we call this a cospan cone. So we call this a cospan. We call any cone on this diagram a cospan cone. And so we have the standard construction of the pullback, so sigma x in A, sigma y in B, fx equals gy, and properties. What we do is we state the universal property of a pullback cone, which is that, I guess this was bad planning, but if you have any cone, any cospan cone, so any cone on that cospan diagram, sorry, let me go backward, let me go the other way. If you have any map, so if P is a cone on that diagram, and you have any map from X to P that induces a cone, right, another cone on the same diagram. And the universal property is just that that map is an equivalence. Okay, so in sort of type theoretic terms, it's pi x.
Well, I don't think you want to put the equivalence sign on the arrow between X and P.
Okay.
It's equivalence between
Yeah.
maps to P.
Let me do it. Yeah. Sorry. Yes. Sorry. Good. Sorry. So it's so maps to P, and what I'll write as, well, guess what I'll write as cone. I'll sort of use this notation. So in Coq, the notation we call this cospan cone FGX, the arguments in that order. But it's that this is a weak equivalence where this is just the canonical map. So in our formalization, it's like map to cospan cone. Okay, so take that. Right. Okay, so for every x, that's an equivalence. Okay. So this is this quantifies over the universe in an essential way. So in other words, if you're proving that if blah 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 has the universal property, then something else does, then you're using quantification over the universe in an essential way. But we showed that this universal property is equivalent to another one. So let me tell you what the other one is. Okay. So if you have any cospan cone, well, by the universal property, we showed that the standard construction has the universal property. And so by the standard construction of the standard, by the universal property of the standard pullback, there will be a map from P to the standard pullback. Right? In fact, it's easy to see. I mean, given any element in P, just take it to the element that, in A, B, and then the proof that they're equal.
Sorry, what does standard mean?
The standard pullback? So sigma x in A, sigma y in B, proof that fx equals gy.
We heard you say that before as you were writing P.
Yeah, I'm sorry. OK, so now PB I'll use for the standard pullback. And now I'm giving the universal property for an arbitrary P. So so given a cone on P, now let me give the universal property of that cone. Yeah? So the universal property is this. Take the canonical map from P to the standard pullback. If that's a weak equivalence, or if that's an equivalence, then the universal property says that P is equivalent to the standard pullback via that map. And yeah, in our formalization, this has the crazy name inv map to pullback to cospan cone. Right, because, so the canonical thing is, right, so here's the map given a map from PB to that, right, it induces a map to the cone, and this is the inverse map of that. So yes, we did, right.
So now that P is no longer the pullback, what is P and what hypothesis on P makes it?
So P is an arbitrary type. So given any cone, right, we say that that cone has the universal property if this induced map is an equivalence.
So this is a definition.
This is definition. Well, it's this. We say it has the universal property prime.
Isn't this the same thing you just did up here with P and X? Now you're doing it with P and PB?
No. So this says for arbitrary x, and this goes. So it's not. They're two different statements.
There are two different properties for a code. Property number one is a property number one. Property number two is a property number two. And theorem says that they're equivalent.
Yes. Thank you, Vladimir. Right. So there are two ways of defining universal property. OK. Yeah. And so we formalized this equivalence. And if there's time, I'll say more about that. Later. OK. Another thing that we formalized, to get things going, is the notion of a map of a cospan cone. So maps of cospan cones. So if you have, let's see. So here's one such cone. Here's another one. A prime, C prime, B prime. Right, so F prime, G prime. Right, so a map of cones will be maps of the corresponding types plus proofs that these squares are commutative. Right? So we formalize the notion of a cospan map, and then composition of cospan maps and the identity maps and so on. And all that goes into showing the functoriality of the standard pullback construction. Right? So if you take the standard pullback of this cone and then the standard pullback of that one, well, there's going to be a function from the first standard pullback to the second. And if you compose the standard, so the function corresponding to the composition of maps is just the composition of the maps. Yeah. You can fill in that, right? So we have functoriality along maps between cones.
Do you need to define the notions of commutative Q?
No. Did we? No. No. So we have commutative square there, and that's, yeah.
Because in category theory, or higher category theory, you may have a cube where all the face commute without the cube commuting itself. You need sort of to put an extra cell inside, a little bit like for commutative.
Yeah, I mean, so in proofs, so we will actually have to prove sometimes that maps, that the corresponding things are, so that the corresponding proofs, the corresponding cells are equal. But we didn't have to break out. So I should say that a lot of what we're doing is sort of at the level of two categories. I mean, so we deal a lot with paths, but by the nature of what we're formalizing, we deal a lot with paths and paths between paths. But for what we did, we don't have to go much beyond that. So really, I'm reporting on sort of that level of.
But even in two-category theory, I think the problems arise of defining what is a commutative cube.
So it may be that implicitly we're sort of dealing with these things without having sort of broken out and formalized and defined the notions. Yeah. But so later I'll describe the kinds of things, the kinds of headaches that we have, and they're exactly those kinds of issues, I think. Okay. And so maps of cospan cones, and we have the functoriality of the standard pullback construction. We also formalized, and this will come into play later, what we call the concrete double pullback lemma, right? Which says this. So given, let's see. So given a diagram that looks like this, right? So take the standard pullback of the first diagram. Then take the pullback of this thing. And what you get is equivalent to taking the pullback of F with the composition. Okay, so essentially that the composition of two pullback cones is, again, a pullback cone relative to the standard pullback construction.
Mind you, I don't know, all of these pullbacks are homotopy pullbacks.
Yes, I should say. So I should say in terms of terminology. So we made this. So initially, when we were formalizing, we said homotopy limit, homotopy pullback, and we made the decision after a while to just drop it because everything is homotopy. Right. So I will just keep using the terminology limit, pullback, and so on, but stick homotopy in front of it. But yes, so the important thing is that it's not just that reasoning about the composition of maps. And when we talk about composing two cones, you're composing maps, and you're also building so you're building the identity proof on the bigger rectangle, which is going to be put together out of that information. And so everything we do, this I'll come back to later, but everything we do, you constantly have to worry about not just the maps, but what you're doing with the proofs and reasoning about what proofs are equal to what.
I'm a little bit confused about what's going on here. Are you doing these proofs axiomatically from the vibration category axioms, or are you doing them?
No, we are proving in Cook, but basically using just this.
The logical system is no different from what everybody else has been using. And these things are already known in that logical system. So what's new about this? I don't.
This is.
I thought if you're working axiomatically, I would understand why it might be.
Well, I'm not sure I understand the question. We are proving them axiomatically from Pising.
Not from the vibration.
Not from the vibration category, from these rules.
From those rules, but those are the same. That's the same attitude that we use.
I mean, my understanding is what's new is the formalization.
Yeah. So I'm not claiming. So like I said, we're formalizing elementary homotopy theory. So it's homotopy theoretic facts.
What's new is that it's now written in the moment.
Yeah. Right.
This kind of material is already in the standard hot library.
No, it's not. No.
It's actually a lot of work. I did a little bit of it myself in Year 0, and I remember
Yeah.
worked quite hard to actually write down the actual formal rules
Yeah.
of all of it.
Yeah. So all our files will make publicly available. I mean, all told, our last count is about 4,500 lines of formalization. So it's just a lot of. I mean, these proofs. This particular proof I just did. This is no great shakes. It's not very hard, but it was work and it was done. Another thing we proved is the abstract double pullback lemma. So not mentioning the standard pullback, but that would be the statement that if you have, so replace this by just two cones, P1 and P2. Right? And so this would be the statement that if this bottom cone is a pullback in the sense of having the universal property, and the top cone is a pullback in the sense of having the universal property, then the composite cone is, again, a pullback in terms of having the universal property. And this I hope to discuss later. This turned out to be a lot of work. It was really a tremendous amount of work, far more than we would have expected. Because you're reasoning about, well, I mean, I'll say more about it later.
Because it is without univalence. With univalence, it would be made much simpler. But if you were able to say that all the Weak equivalences there are just equalities, then you would eliminate, I mean.
That's right. But
this is kind of, this is doing by hand what eventually the constructive interpretation of univalence
should do.
Numerically.
So it's a good motivation for you.
It's a good, so pointing to the pain involved, right?
Like
Right.
working with all the
Yeah.
extensionality.
Yeah. Right.
You're
Yeah.
just saying specifically the constructive interpretation of univalence would make this easier, or just the univalence as an axiom?
No. The univalence as an axiom makes it easy.
How?
But then the proof will contain univalence as a constant. Now, then if you have constructive interpretation of univalence, you can take a proof, simple proof with univalence. You can eliminate univalence out of it. You'll get a proof without univalence. So basically what you guys did by hand.
Is it really obvious that it's univalence as an axiom?
Well, it's easier because of this equivalence of the two conditions over there. Because, for example, here,
Once you have the concrete one and the equivalence, you get the absolute.
you have this, that if something is an abstract pullback, then it's equivalent to the concrete pullback.
Yeah.
So this equivalence will become an equality. And so every time you have an abstract pullback, you can just eliminate along this equality to concrete pullback and then apply the previous result.
I think it does make, I think it would make it somewhat easier, but there are still some bits which need to be involved in terms of checking that say the map induced by transport along the equality that comes from univalence is the same map that one is actually wanting to show as an equivalence. And one wants to show some map as an equivalence.
Yeah, because remember, the universal property is not just that they're equivalent, but that a certain map is the equivalence.
I mean, I think it certainly would make it somewhat easier, but I don't think it quite makes it reality.
Well, I don't know. That might be an interesting thing to try. I mean, it depends on how hard it is in present state, whether it will make it much easier or not.
Yeah.
How hard it is.
You say that this abstract double pullback is a difficult endeavor.
It was,
But
yeah.
is it a key step to make things easy afterwards?
Yeah, so in fact, we broke it out pullback 3 because it never gets used anywhere else in our formalization. and pullbacks through. So I'll tell you, we basically proved it once. The tactic proof, Cook accepted, and then died on the QED, on the defined. It just killed Cook. So then we did another one, which was a lot of work. Took a very long time to compile. Then we got a third proof that is a lot nicer. And actually, so the third proof actually gives the stronger property that if given that the bottom square has the universal property, then the top one does if and only if the full rectangle does. And so that's what we ultimately have a proof of.
I think it's an important kind of stuff because, for example, we're working on this new proof of system, and we'll need some kind of test case for it to run, for example, like substantial ones.
We also need the fading cases.
So we'll save them. Yeah. So everything is this whole.
I hope it's all saved.
What?
I hope it's all saved.
Yeah. Well, we're using we're using Git, so it's everything is available for until the sun burns out. Yeah. But so and in fact, I'll come back to this later. But I think we just have an idea for a fourth proof that will hopefully be easier. So we keep coming back to this to try to understand. So I think this is that was a good test case. Just moving on with pullbacks a little bit. So that was in pullbacks. Pullbacks 3, as I said, is the abstract double pullback lemma. Pullbacks 2 just has some examples. And so just for examples of what you can do with pullbacks is, so first of all, we observe that you can think of an H fiber as a pullback. So if you have B, A, and sort of the name for an element, I guess you write it like this, A and A, then if you take the standard pullback, we show that the standard pullback of that diagram is equivalent to the homotopy fiber over A. Yeah, so that's one example. Another one is loops as pullbacks. So there's a reason to mention these. They will come back later. So if you have, let's see. So here, you pick an element A, right? If you take this pullback, you're getting the loop space of A at A. So in other words, the type, you're getting something equivalent to IDA. Sorry, this is just the one. This is my bad handwriting. It's a 1. It's just the unit type. Yep. And so this is just the constant map. Element A. Okay. So formally we show take the standard pullback of this, and it's equivalent to that. And also just again exercising elementary homotopy theory, we show that. So you can define. So we give an independent definition of the standard equalizer. But we show that if you do the pullback construction of an equalizer, right, you get the same thing. You get something equivalent, and also vice versa. That you can use equalizers to construct pullbacks. Okay. And that's it for. So that's what we do with pullbacks. And the nice thing about limits. So in a moment I'll tell you about limits. So basically we construct limits over graphs. But the nice thing is, as soon as I tell you what we mean by a limit over graph, everything that we do for pullbacks just sort of carried over to the more general saying. So the limits over arbitrary diagrams, this is just a particular kind of diagram. What? Yeah? OK. Right, so in dealing with limits, so here's the Cook definition of what a graph is, or something like it. So here. So here we use, I should have mentioned in the beginning, I said that we use sigma types. Sometimes instead of an iterated sigma type, we just use a record type, which formally you can think of just being just syntactic sugar. There are times when sigma types, iterated sigma types, prove to be more convenient. But there are also times, it turns out if in Cook, if you iterate 4 or 5 sigmas, Cook dies pretty quickly. And so, so for efficiency reasons, there's some things that we formalize as graphs. Here, this is just one dependency, so this could have just as well have been a sigma type. But I guess for coercions, or I don't know, we could have done it either way, but here we define it as a record type. But a graph has just two components. So the first thing is an underlying type, which we call graph 0. And this symbol means it's coerced to a type. So if you have a graph, so formally it's a record, but if you treat it as a type, the system will notice it's just to take the projection to the first component. And the second component, also we give a conversion. So these are the sets of arrows between elements of the graph. So these are the edge sets. So given two vertices, two elements of graph 0, it just gives you another type. Yeah? OK. So what this means is if G is a graph, so on the one hand, this coercion means you can treat graph as a type. So you can talk about the elements of the graph. But it also means that if I and j are elements of the graph, you can write Gij for the type of edges between I and j. And that worked out pretty nicely. And then a diagram on the graph. Again, it's got two components. So there's the first component is, so for every element of the graph, for every vertex, you need a type. So it's a map from G to type. And implicitly, the coercion is, so it's really the first component of G. And then the second component is a proof that so what is it? It's a proof that it's for every element, for every arrow between two elements, it gives you a corresponding function between the corresponding elements of the diagram. Okay, so it goes from, so it takes two vertices and gives you a function from the set of edges between those vertices to the space of functions between the diagram at I and the diagram at j. Yeah, so the picture is, so G, think of as being a bunch of edges. There's I, j, and there's some arrows between them. And then the diagram gives you a d of I corresponding to each I, a d of j corresponding to each j. And then for each arrow, so there's a function which for each arrow gives you a corresponding function between the types. Okay.
That's a strange definition for sure, because where are all the commutativities?
Right. So this is the key point. So this is just a free graph, right, which basically gives you the free category. So here's what my guys trained me to say, right? So right now, right, so these are just the simple limits. Right now, this is the best we can do. And so the issue is just the familiar one. So that if you try to formalize the notion of a category, in addition to saying, you've got these objects and arrows, then you would have compositions, you would have identities, and then you would want to start right down. You want to say that, for example, the composition is associative. And the problem is that in homotopy type theory, you can't say associative on the nose, right? It's only up to homotopy. Then, if you have 4 arrows in a row, there are different associativity ways of getting the same thing. You want to say that those are homotopic, and so on all the way up.
May I ask something? Just to have an example to get a feeling. Suppose my graph is a triangle.
Yep.
So I have 3 vertices and 1 edge from 0 to 2, and 1 edge from 0 to 1, and 1 from 1 to 2.
These are directed.
Yes.
0 to 1.
Triangle.
Right. So triangle.
And then I have gadgets then I have a diagram over it.
Yep.
And will then the
No,
commutative.
there it doesn't commute.
It's a
They don't
commutative
commute.
triangle.
That's what was confusing me.
Yeah.
Okay, sorry.
Yeah. Yeah.
Just a graph.
But moreover, so Peter's also went out of his way to train me to say the following. So even though for a fixed, even if you fix your categories, some fixed H set level, and you just soldier through and you write down all the coherence, which in principle, could be done. Even if you restrict attention to that, and so in principle you could formalize the notion of category, you would still have trouble saying arbitrary diagram. And you're talking about arbitrary diagrams on that category. Because again, you want to say that the diagrams respect the relationships in the category. And again, you can't say that up to the nose, so then you have coherences all the way up. So there are serious problems for talking about arbitrary diagrams and arbitrary categories. And so this is where we need somebody smart, like Peter, and people here, to figure out how to talk about, right. So we don't have that. So this is just the very simple case.
You can go to graphs just quick though.
Yeah. Right. Yeah. And it goes through, and the good news is that it goes through very smoothly. So everything, I really don't have to put down much of the list. We have the standard construction of a limit, the two formulations of the limit, the universal property, the proof of the equivalence, maps of, instead of maps of cosine cones, maps of diagrams, and functoriality of limits over diagrams. Everything works out.
May I have another example?
Yeah.
What if my graph is the vertices of a graph are elements of a group, and edges of the graph are wait. No. Let's take. No, it doesn't work like that.
At the moment, this isn't a rich enough setting to be able to encode the group structure.
Yeah, I was thinking about how to get homotopy fixed points somehow.
No, yeah. Okay.
We were thinking too, but
If
we haven't figured it out.
Yeah. Okay. Yeah. Okay.
There is one case of a graph which maybe is worthwhile to look in.
Uh-huh.
Is the case of a graph with units. For
Yeah.
example, in the notions of co-limit or limits equalizer with reflexive co-equalizer, or
Okay.
reflexive equalizer, is very important. And this notion does not involve any problem with coherence. And I think that you could probably do that, also extend what you have done to graph with units.
So bumping graphs up to reflexive graphs.
Reflexive graph. Yeah.
What is a graph with units?
It's a reflexive graph. It has
How does it give you reflexive equalizer?
I'm sorry?
How does it give reflexive equalizer?
Doesn't a reflective co-equalizer also still talk about composition?
Well, it means composition.
Yes, right. But the reflexive equalizer or co-equalizer can be constructed in homotopy type theory, I believe.
It's actually not real issue, because reflexive, for example, reflexive colimits are universal, right? I mean, they're kind of well behaved. But I don't think that the homotopy colimit of a reflexive co-equalizer diagram is the same as the colimit of this diagram.
I agree with you. But
So in that case, there are two different ones, and it's not quite clear which one to choose. And both of them are well defined.
right. But what I'm saying is that the homotopy colimit of reflexive co-equalizer diagram, I think, can be described in the language of homotopy type theory, at least if you have higher inductive type.
Oh yes, I have that here.
One
without and with no.
I think one way to see that and why
It's an
this
interesting thing. I don't know.
is if one bumps this up to two computeds or two semi-simplicial sets or something, then one could describe a general setting where one could take limits of this form without a coherence problem, and that would include the reflexive co-equalizer case. So I think something like that, the category of a reflexive co-equalizer is not free on a graph, but it is free on a two computed.
Okay, let's maybe move this discussion until, yeah? Okay, let me yeah, oh, no, it's quite all right. Okay. And again, just exercising this elementary homotopy theory. So we have the standard construction of the limit. We also show that the standard construction of a limit in terms of pullbacks and equalizers gives you something equivalent, right? So we can actually, we have pullbacks, we have equalizers. So we can write down that construction and show that's equivalent to just the straightforward definition. Let's see. We also prove it's very easy to prove that limits preserve H levels. So if you have a diagram and every type in the diagram has H level n, then the limit has H level n. That's a 3-line proof. And then also, just sort of as a reality check, we show that the pullbacks and equalizers are limits in this sense. So for example, for the pullback, you construct this graph, right? And if you put the data on the diagram and take a limit, then what you get is equivalent to the limits that we had the pullbacks that we had up there. Okay. And finally, so I'm just about done giving you an overview of the library, and I can then say a little bit more, give you a little bit more details of the formalization. Again, exercising pullbacks and limits and so on, we define pointed types, and then we use pullbacks to give a slick proof of the long exact sequence theorem. But rather than spell that out now, let me do that a little bit later, and I'll give you a little bit more detail of that. Okay, so we have sort of a nice little application to elementary, in elementary homotopy theory. Okay. Okay, so this is, yeah.
So one graph which can probably be interestingly applied would be natural numbers with the inverse order, right? Or something like
Yes.
that.
So.
And that would give you the homotopy pullback of a tower.
Yeah. So that's the only place that. So in examples, it's the only place that we're with. So right now, we've actually written down a definition of that graph. So we have it. There it is. 0, 1, 2. That's the only thing we use the natural numbers for. So we have the graph, and we haven't done anything with it yet. But the graph is there. We've defined the graph. So, but yeah. Okay. Very good. Okay. So that's an overview of what's there. And now, for whatever time I have left, what I'll do is let me spend some of my time just giving you a little bit more detail about the formalization and sort of observations on what was difficult and what was easy and things we learned about how to go about doing things and how not to go about doing things. So this will be kind of impressionistic, but I at least try to organize our thoughts in a coherent way. Let's see. So let me go. So one of the things that really takes a lot of getting used to is this whole crazy proof relevance business. I mean, you're used to, if you've done interactive theorem proving, you used to, you prove an equality and, you finish the proof and that's it, you're done with it. But, now you find you're in a situation where later on you have to open up that proof and reason about, right? I mean, that proof is really a construction. Then you have to open up and reason about that construction. And so hacking through a proof is just, you just don't want to do it. You want to find the right proof because it's, you're going to need to use it later on. So that, that takes a lot of getting used to. And the other thing is you have to get really good at reasoning about path constructions. I mean, you've just got these constructions of paths, and you've got to prove things about them. And so let me say a little bit about when it comes to formalization, the kinds of things you have to cope with. So along notes and observations. So the first topic I want to spend some time is talking about paths between elements of dependent types, and more generally complex types with dependencies. So dependent types. Right. So I'll remind you briefly that if you have a sigma type, right, and you have two elements, say A1, B1, and A2, B2, and you want to construct a path between them, right, what you have to do is first you have to construct a path from A1 to A2. And then second of all, so first transport B1 so that it sits over A2. And construct a path from the transport of B1 along P to B2. This can get pretty complicated. And moreover, the real problem is transport is not very informative. If I say, give me an object of type transport blah, 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 something transported, you're not going to know what to do. Transport is just too general for the library to have any useful things to tell you about what to do with it. And so typically, whenever we had all these types I described up there, the first thing that you have to do when working with them is figure out exactly what should morally count as the right canonical way of constructing an equality between them. Show that that really is equivalent to doing this. And then you use the nicer formulation of the equality lemma. So let me just give you 3 quick examples just to give you a feel for that. So the first idea is that you want to sort of analyze exactly what it means to what you need to do to construct a path. And the other trick that we found useful is take the list of data that you need to construct a path and bundle that up into a type so that you can state a lemma saying that, look, if you have all this stuff, you have a path. And that's useful in a tactic style proof. When you're trying to construct a path, you apply the lemma, and then Cook happily comes back and says, OK, you just have to give me this bundle of stuff. Okay, so it's really sort of analyzing and bundling and just doing that repeatedly. And then, again, building lemmas that will let you construct those sorts of things once you've figured out what they are. So just to take a simple example. So coming back to our old friend, the pullback. Right, so here's example 1. So remember that the pullback, so now using something like the Cook notation in the homotopy type theory library, right, is defined, so it's a sigma type. You take an x in A, and then you take sigma y in B, and then fx equals gy. Okay. Right, so an element of this is an x and a y, and then an alpha, a proof that fx is equal to gy. And then if you have another one, it'll be something like an x prime and y prime and an alpha prime. Right? And so this is an iterative segment type. So if you just use something like this blindly, it's path, transport, and double transport. And that's not what you want. So let's think a little bit about what it takes to get a path between these two things. Right? Well, first, of course, you need a path between x and x1. So yes. So in fact, but if you just used the generic construction and the generic lemmas, you would get these transports then that don't do anything. Right? So the next thing I was about to say is that in this case, you get a simplification that the second component, in fact, in this case, there's no transport. And you want to use that fact. Right? And then the third component, right? So what you want is a path between alpha and alpha. A path now between alpha and alpha prime suitably transported. And if you think about what that should really mean, so alpha. So alpha is a proof is a path between fx and gy. And alpha prime is a path between fx prime and gy prime. But look, you're assuming they've already constructed your path p from x to x prime. So this, so let's see, map fp. So you have a path from fx to fx prime. And you also have, so map gq, you also have a path from here to here. And so one would guess that what you really want to do is show that this, instead of this double transport, what that amounts to is showing that this square commutes, right? And in fact, so one shows that it's the case. So to construct a path between these things, you construct a p between x and x prime, a q between y and y prime, and then you need an element of, so map fp. So exclamation mark is the opposite. So from there to there to there. So take that, concatenate with alpha, and concatenate with map gy. You want that thing to be equal to alpha prime. Right? And so that's the third component you need. And let's call that R. GQ. Okay, so that's exactly what our lemma says. It says to construct a path between these things, give me a P, Q, and R, no transport. And this is good because you know a lot about map, you know a lot about opposite, right? If you see these things in front of you, you know what to do. These are things that you can work with. Let me just give you two more quick examples.
So your conclusion for this one is that you don't have any transport anymore in the formulation.
That's right. Right. So if you just used a generic lemma, you'd have all these transports. But now, and I mean, you've used the J rule to prove this equivalence, right? So you use the J rule when it's easy to do. Now you have this nicer formulation. You don't have to worry about it later on. Okay. To take another example, that's not too much more complicated.
Probably have any equivalence between the type,
Yes.
identity character, proofs of one kind, and other.
That's right. That's right. And we don't even need that fact. We don't even have to think about that other type. But yeah. OK. So example number 2 is not too much more complicated. But so remember I said that given data, the usual pullback data types A, B, C, and an F and a G, right? You need to talk about cones on that data. So a cone is a sigma type. So a cone on the data, A, B, C, F, G. So this is what we call cospan cone. So if you just give FG, Cook can infer A, B, and C. So this is our notation. But that type, so an element of that type, so it's a sigma type. So it consists of so the H from X to A, and the K from X to B, and then a proof that for all X, F of HX is equal to G of KX. What is that? Okay. And so now the question is, suppose I give you two cospan cones, HK alpha and H prime K prime alpha prime. I'm going to do it this way. The question is, what do you need to do to show that the cones are homotopic? Right? And this you're going to have to do a lot, because all our universal properties, they talk about this map for cones. So you want to show that if you take a cone and you do something, then you map back, that you get the same thing back. Right? You always have to reason about this cone is homotopic to that one. So you're going to have to do this a lot. So the question is, what's the canonical way? How do you construct the data to get that homotopy? And the observation is, if X is just the unit type, then this is really just an element of the pullback. So it's going to look a lot like that, except it's kind of parameterized by X. Okay. So here's what it comes down to. Right. So the first thing you're going to have to do is show that H is equal to H prime. And by function extensionality, it doesn't matter whether you say equals or pointwise equal. And so we use, we say equal. So you want to give a P going from H to H prime, and a Q going from K to K prime. Yeah. And then, well, rather than reason it out, let me just say that you want to basically take that idea, but you want to make it parametric in X. And making it parametric in X is taking this path P, turning it into a pointwise path for any X from H of X to H prime of X. So that's what H apply does. And then doing that trick. So the last piece of data you need is now parameterized for all X. So you take the opposite, so map F. So instead of mapping F onto P, you map F onto H apply Px. Right? And then you concatenate that with alpha X. And then you concatenate that with map of G of H apply Qx. There. Do all my parentheses match up? Yeah. OK. Right. So this is a canonical. So constructing a cospan cone, you do this, you do that, and then you have to construct something of this type. And in particular situations, all these things can be instantiated with things that you constructed in other places. But this is pretty good. I mean, the library has a lot to say about happly and has a lot to say about map and how happly and map interact with concatenation and opposite and so on. So, you faced yourself trying to construct something of this type, but there are things you can do. Right? Your library, so you've got enough facts about these basic constructors that tell you, that give you something to go on.
That's a particular simple example of a commutative cube. This thing.
Yeah.
It's a commutative cube where only two faces are not triggered.
OK, so very good. So we were dealing with it implicitly. But as I said, if you ever get to the point where you want to do sort of three categorical type things, you're probably going to have to expand your library with a palette of how you cope with these. You're probably going to need identities like this on sort of the next level up. Yeah. And just for let me just one last quick example. So this is example 3. I'll just wave my hands at it. But I mentioned that we have a notion of a cospan map, right? So if you have so this is before when I say you have an F and a G and an A prime and an F prime and C. And C. Right, so a cospan map M, right, from there to there, consists of 5 components. It's a map from A to A prime, a map from C to C prime, a map from B to B prime, and then proofs that the corresponding squares commute. Well, suppose you have another one, M prime. Right? We want to talk about compositions, and compositions being homotopic to the identity. Right? So you need to say what it means for two such things to be equal. Well, there are going to be 5 components involved. 2 things are equal if each of the component maps is equal. And then the induced, whatever's going on with those commutative square proofs, those have to be the same as well. And so just guys, suck it up, write down, figure out what it is, write down the definition, bundle up in a package, and that's what you need. But you've got to do it, right? And that's what you can use. And so if you look in our files, you find exactly a type of something called, what's it called? Cospan diagram homotopy, or something like that. It's a record with 5 components, and it tells you, and there's a proof that if you have these 5 components, then you have a path between M and M prime. OK, so that's the first bit of reflection I wanted to give you on the formalization process. You need to sort of think about these constructions and package them up nicely. You need a certain amount of facility with path algebra, messing around with map and happly and concat and funnext and so on. In terms of tactics, there are a lot of tactics in the library that will sort of search and do lots of reasonable things. In the end, we found that they were sometimes helpful in filling gaps, but they usually slowed down the compilation a lot. And so in the end, we really didn't use the tactics a whole lot. We just basically got used to doing them by hand. And yeah, OK. So I think that's the first part of am I supposed to go until 12:20 or how long? 12:30? OK. Yeah, very good. OK, so the next thing, I'll basically just keep going until I run out of time, and then I'll tell you what I would have said in the remaining time. So what I want to do is, I hope this isn't heavy-handed, but I want to just sort of discuss sort of general strategies that we found to be useful in formalization. And then maybe I'll talk about a particular proof in the remaining few minutes. So I just wrote down some notes about general strategies. Yeah. Right. So the first thing is when you're formalizing, you want to modularize. Right? And people will tell you, this is, if you're coding, if you're doing any kinds of formalization, modularize. So in a sense that there's nothing really new here, except it takes on added significance when you're doing homotopy type theory because of this whole proof relevance business. Right? So there are 2 reasons why it's particularly important to do it here. One is that if you don't have the modules you need, if you're sort of working through the proof, you might find that you need an identity that you can't prove in line, right? Because the only way to do it is to generalize and apply the J rule or something like that. right? So you really need to sort of break out the things that you need. And so either you have the foresight to figure it out ahead of time or guess ahead of time, or you're doing your proof and then it hits you that there's something you need. But you really have to break them out in that way. So one is that you can't always do it in line. And the other reason it's particularly important here is, again, if your proof isn't modular, you've got proof relevance. It's a construction, and later you're going to unpack the construction. And when you unpack the construction, you're trying to prove something about a proof term. Now, if you're modular, then your proof term is simple, expressed in terms of these things that you can then unfold if you need to. But you'll have lemmas about these higher level things, and then when you unfold them, then they'll also things about lower level things. But you've got sort of an organization where you can figure out how much you unfold and what you need to do. If you haven't modularized, then you're trying to compare two terms, and they're just huge. I mean, they just get gigantic. And so it's much harder, if not impossible. Right? So that the fact that proofs are relevant. Okay. Let's see. And so along the same lines, you want to build infrastructure. So whenever you sort of formalize a basic concept, sit down, try to think of all the things you might do with it. You're not going to get them all. Later on, you're going to figure out other things. But build a good library before you try to do anything useful with it. And the last thing builds on these. So this is why it's good that I was working with Peter and Chris. You can't expect too much from the interactive theorem prover. I mean, if you don't know how to prove something, it's not going to solve your problems. You really need to sort of find the right proof, which is to say you need to find the right way of thinking of it in homotopy theoretic terms or in categorical terms where the concepts really are modular. And you can see this as composing this with that and the other. And so when I say that you shouldn't expect too much of the interactive theorem prover, that's not to say that Coq was not helpful. These things are kind of really fiddly and hard to keep. So Coq is very good at helping you keep track of your definitions, right? Keeping track of what you're doing and telling you what it is, sort of guiding you what you need to do. So you need to set it up and get things right. But Coq is really, really good and helpful in keeping track of the administrative details. Okay. So let me, in the last, let's see. So the remaining things I was going to talk about are, I was going to show you a proof that the two universal properties are equivalent. Let me leave that out. The other thing I was going to talk about is this abstract double pullback lemma, which I mean, as you can tell, we're kind of obsessive about it. So I was going to talk about the different approaches that we tried and the ones that finally worked. But
Can I actually say a few words about it? Because I would like to, maybe very, very superficially, because I would like to have a look and see where univalence would have simplified things. Maybe we could.
I think that's a very good, yeah. That would be very interesting. I think we should. Yeah. But let me just try to do one more thing before we close, and that is tell you about the long exact sequences, because that really sort of illustrates how the various components of the library were sort of put to use in an interesting way. Okay. And so when you talk about long exact sequences, you really want to do it in terms of pointed spaces. So long exact sequences. Right. So we did formalize the notion of a pointed space, but it's just it's a sigma type, or maybe a record, right? But basically, a pointed space is just a type, and then an element, a point of that type. Okay. And of course, we coerced the first component. So if X is a pointed space, you can treat it like a type. But then you want to talk about pointed maps. And so I'm told that Benedict suggested this useful notation. So here is our notation. Well, here's our notation for a pointed map between spaces. So this is the type. An element of this type really consists of an f from x to y, and then a proof that f x0 is equal to y0. So it's really a pair.
Well, I have a question. dot in coq without conflicting with the end of the sentence?
Yeah, notation will.
Is that a problem?
Yeah, notation, coq notation.
The dot, if it's not followed by a space,
Yeah. I see. Okay.
It does mess up the electric period terminator Emacs if you have to use that.
Yeah, that's a bad idea anyway, so.
Yeah.
If it's not followed by a space, then it doesn't conflict at all.
Exactly.
Cool. Cool. That's good for us.
Okay.
We'll make a macro anyway.
You're
welcome.
You decide to do it.
Yeah.
Well, it's exchange of experience.
Right. So a pointed map is really an element of a sigma type. But once again, it's nice that you can have a conversion. So if you have a pointed map, you can just apply it like a function and treat it as such. OK, so here's my limited understanding of short exact sequences. So again, this is one of the places where you really have to bear with me. But so short exact sequence. OK. So to start with a pointed map between pointed spaces. So really, there's an F, P, and this is really E, E0, and B, comma, B0. And so let's see, there is a natural inclusion of the pointed fiber of this map. So this is the fiber H5 of F B0. So it's the fiber of F over B0. And then the natural point here, element there, is just you take E0 and then P, right? Because P is a proof that F of E0 is equal to B0. Okay. And so more generally, something is a short exact sequence if F is equivalent to that, more or less, or something. Yeah, OK. Yeah, so here's, right. So the long exact sequence theorem says, take such a map of pointed spaces, right? So if this is a short exact sequence, and you have another one, then the thing here has to be equivalent to the loop space on B. Okay, and this is again a short. So another way of saying it, if you take this, this is again a short exact sequence, right? And then you can iterate that, so you get omega E, omega F, and omega squared B, and so on.
Just a comment.
Yeah.
I would think homotopy theorists would more like call this a vibration sequence.
Okay. So
Yeah, vibration sequence is better than short exact.
we had the file was called vibration sequence. Let me change the name. I know. Should we change it back to vibration sequence? We should discuss it in private. Yes, in camera, behind closed doors. Yeah. Anyhow, let me just tell you the theorem that we proved and how we proved it, and then we can be done. Oh, sorry. Yes. OK. So the theorem that we proved is exactly this. So start with a pointed map between pointed spaces E and B, right? And then what I'm about to say, let F be the pointed H fiber of F over B0, so the pointed version. Okay. So the theorem is that the H fiber of the inclusion of F, sort of the pointed inclusion of F in E, is isomorphic to the pointed loop space, so at B0. I don't know where to put it, B0. So it's and that this is an equivalence, yeah. So this is the theorem, right? So we formalized all these notions, and the theorem is exactly this.
already proved that?
I don't know.
But
You did.
but you know what? I'm thinking about something like that right now.
OK.
I think in the future, there probably will be like works dedicated specifically for building a better library for something which has already been done. This is inevitable.
Yeah.
I mean, because building it with more efficient computation with better lemmas which can be more convenient to use. This should be part of the process of moving forward, redoing something.
Yeah. So we really did this as a test, an illustration of
And
the
also, yeah,
the things we'd formalized.
Various formal proofs. I have this dream in mind of doing some interesting kind of structural analysis, statistical structural analysis of various approaches to proving things. And that's I think also.
So let me show you the proof. Let me show you the proof we did, because it's really kind of cute. So this is a proof that Chris discovered last year, and has since determined that it has appeared in the literature. Chris, what's the citation? Who first? Some guy somewhere.
Pullbacks in homotopy theory, Michael Matter, I think. And it's like a funny paper because he says, you know, there are these quasi-categories, but nah. When you read it from our perspective.
Yeah. Okay. So here's Chris's and this other guy's proof. So you start with you map f from E to B, so it's pointed. But so here let's stick the point in there. So the point in B is that, and f takes E0 to B0. And so I've already told you that you can think of the fibration of f over B0 as the pullback here of this diagram. Now, what the recipe says is now you've got to look at the fibration of f over E. So again, we know how to do that. I mean, in E, you have the relevant point E0. And what you do is you look at the pullback of this square. So this will be exactly that thing, right? The fiber of f over E. Oh, but look, our double pullback, the concrete double pullback lemma says that this is equivalent to taking the pullback on this bigger square. But what's going on in this bigger square? Well, there's a 1 here. There's a 1 here. I mean, this B0 is equal to f of E0. Right? So this, I've already told you earlier, that this is exactly the loop space of B. And that's the proof. And Chris likes to just keep going with this. So what do you go? So then if you want to get the next, you sort of take the fibration going this way, 1, and then you sort of pull it back, and then you get that thing, and then you sort of go up. So you stick in 1 there, and you take a vibration that way, and you get, this is omega E, omega F. So you can sort of keep going back. But the core thing is that really we get this as just sort of a nice application of all the things we had before with pullbacks and the double pullback lemma, and then the particular characterization of fibers and loop spaces as pullbacks. Okay, so I think this is a nice place to end the talk. So thank you very much.
So yeah, we don't have 5 types, and we need way more structure, right? We don't have all pullbacks in vibration categories. Sorry. What have I just said? Yeah.
So I mean, you don't.
In our case, say all objects are co-fiber.
Yeah. So you don't have the J rule, right? So it's not right. So strictly speaking, we're right. We have to. So we add that, right? I mean, so the factorization with the path object, and is that kind of like a? So what's the way to think about that?
So the J rule is a bit more than just having that factorization. And the J rule also gives this the elimination rule. So there are a couple of fairly big extra ingredients that we do have on top of the fibration categories. But the kind of idea behind considering fibration categories is that of some of the familiar homotopy theoretic axiomatization, you've got fibration categories which are rather less than this basic type theory, and then model categories which are rather more than this type theory. And so for seeing what we can develop in this basic type theory, we're expecting to be able to port over the things that have been traditionally done using vibration categories. Whereas the things that are traditionally done using stronger axiomatization on the whole, one shouldn't expect to do until one has stronger things in the type theory. So we certainly do have more in the type theory than there is in vibration categories. Yeah. Like, for instance, the elimination corresponding to the weak factorization system.
Wait. Here's my question. So vibration category doesn't assume weak factorization system?
No. Oh, okay. You have a.
I
a question back really being asked. Why don't you add live to why don't you work in the join between a weak
Well, so for a long time, I was pushing them to say, tell me what the semantics is. And they sort of labored long. I mean, you can just say it. But basically, you end up saying, oh, well, that's essentially what I said. I said, well, any vibration category that is actually moreover has the structure to be a model of FML. Just say that. I've just said it.
This is a more specific question, though. Given that we know the weak factorization system semantics for the type theory, and especially the distinctive identity elimination rule corresponds to the diagonal filling condition in the weak factorization system, so we know that's there. What is the advantage of working in this impoverished setting as opposed to just working in the weak factorization system? Or perhaps, as Nicola suggested, the join of the two concepts, weak factorization system plus vibration category.
I mean, for formalizing homotopy theory internally, weak factorization system by itself is not enough because, well, there are no weak equivalences. So you can work in a join, but then, I mean, homotopy theoretic notions are specific to categories with weak equivalences.
I would just say that's what you're asking is a different direction from what we're trying to do.
Yes.
If one was looking more at the semantics, then absolutely, I think that would be the right way to go. But simply what we're doing is internally doing this formalization and kind of being guided by some of the traditional axiomatic developments that exist. So the vibration category thing, that fact is essentially a side part. We're not trying to break new ground in that direction. I'm not saying that.
Yeah. So this isn't. Yeah. So this isn't. So this isn't any kind of. We don't really address this. I mean, just very little. It's not at all a contribution to the semantics. Really, the best way to characterize it is we derive these facts from a weak fragment of type theory.
Just to come back to the talk, but I wonder actually how much do we actually need pi types? I mean, can most of this not done in sort of like first order types theory, or what other extensions of first order types theory you actually need?
So that's a good question.
That is a nice question that we've wondered about a little bit, but not really significantly gone into. The question of how much of this one could get by without typos for. And I think that's a very nice question.
Yeah. And so now at least we have a good library. We can sort of look through the library and try to think about. Yeah. Yeah.
This isn't a question as much as one extra comment that I should say, for the sake of that a lot of the material we've been doing here, especially limits on graphs and things, is work which also Egbert and Buss were doing
I'm sorry. Yeah.
in mathematical prose and taking further in those directions. A lot of the things we've done are the same things that they've been doing.
Yeah. So there is a lot of overlap between the two projects. Yeah. And I think that's good. I mean, I think it's nice that different people are working on the same thing from different perspectives, because then you just sort of get this confluence and this triangulation. Okay. All right. Thank you very much.